Hello, welcome to lecture 20. In the previous few classes, we derived the vorticity equation, we showed the evolution of vorticity and why vorticity can be generated by various mechanisms. We discussed the barotropic and baroclinic fluids, and we saw how the vorticity equation modifies to a simple form in a 2D system. Now, why are we doing vorticity? Because vorticity is of prime importance in higher Reynolds number systems. For example, the systems of our interest, the geophysical flows, the oceans, and the atmosphere. But one of the prime characteristic that has been missing in our analysis till now in the chapter on vorticity is rotating frame of reference. So we have derived the vorticity equation in a non-rotating frame of reference, and now we'll see what happens when we introduce rotation into the system, and that is of prime importance because our frame of reference is rotating, and that actually distinguishes the geophysical flows from the other lab scale analysis. So we will briefly mention how vorticity equation, how vorticity evolves, or what is the form of the vorticity equation in a rotating frame of reference. And to get into to get the form of the vorticity equation in a rotating frame, let us define something called absolute vorticity. We'll represent it by the symbol omega subscript a, and this is a vector quantity. This is vorticity, and this is defined as the vorticity which is due to the rotation of the fluid particle when a fluid particle is rotating about its center, as well as the rotation of the whole frame of reference in which we are measuring. So this has already been defined in the previous lecture. This is the vorticity, or now in correct terminology, this is the relative vorticity. Please remember, because our frame of reference was not moving in the previous lectures, in the previous derivations, we had just loosely mentioned this to be vorticity. But given the fact that now the frame of reference is also moving, we now term this as relative vorticity, because this is the vorticity with respect to the rotating frame of reference. Or vorticity defined in the rotating frame of reference. And this is the vorticity that we will be measuring. For example, there is a vertical motion in front of you. Let's say there is a vortex in an ocean or vortex in a bathtub that you are going to measure. So we are in a rotating frame of reference, and anything that we measure is relative to that rotating frame of reference, because we as the observer is also rotating with Earth. So this is the relative vorticity that we measure, and omega is the angular velocity of the frame of reference. So this is the angular velocity of the reference frame, and we are well familiar with this by now. And this is the frame that is attached to the Earth's surface, and based on which we do measurements in the measurements of the geophysical flows. So as I said, we'll not go into the detailed derivation, but we'll discuss the steps that lead to the vorticity equation in the rotating frame of reference. For this, we will start with the momentum equations in a rotating frame. Start with the momentum equations in the rotating frame. So if necessary, you might want to go back to the earlier classes to see how did we derive the momentum equations in a rotating frame, and we have spent quite a lot of time, so we'll just state the momentum equations here. So we'll start with the momentum equations in the rotating frame, and then we follow the same steps as follow the same steps as done for the derivation of the vorticity equation in the non-rotating frame of reference. Okay, so follow the same steps as we had done for the derivation of the vorticity equation in non-rotating frame of reference, but we have the rotating frame now, but follow the steps are the same. So using definition of omega omega a, that we say that is the absolute vorticity, the vorticity equation in the rotating frame becomes so this is the vorticity equation in the rotating frame of reference, and you can see that the only term that changes in when we compare it to the non-rotating the vorticity equation in the non-rotating frame of reference is this one. This is the term which includes the rotation of the reference frame of reference, and this f equal to 2 omega is we know that f is the variable that is 2 omega. This is the only term that is different as compared to the non-rotating vorticity equation. You might want to compare both the equations. Now remember that in this equation, both vector u and vector omega are relative velocity and vorticity. What is relative velocity and vorticity is exactly, same that we had described earlier. It's the measurement of velocity and vorticity with respect to the rotating frame of reference. So these are relative, in correct terminology, these are relative velocity and vorticity. Now the reason why this material derivative of omega, material derivative of omega a does not appear, but material derivative of just omega appear in the first term is because 2 omega is the rotation rate is constant. I'm just expanding the first term. So if we had, even if we, the original term should have been the absolute vorticity, but this is what, this is dt plus df dt, the total derivative of vorticity, the relative vorticity and f, and given the fact that f equal to 2 omega and omega is constant, hence the time derivative is 0. So the only term that remains is the total derivative of the relative vorticity. Now the viscous term, why should the viscous term not have the absolute vorticity? As you can see, this has the relative vorticity, this is the relative the first term has the relative vorticity, while only the second term, this omega dot del u, has the total vorticity. What happens to the viscous term? So if we have the Laplacian of the absolute vorticity, this is similar to, this is equal to this omega plus f nu del square omega plus nu del square 2 omega. Now, given the fact that 2 omega is spatially uniform, this is spatially uniform, the Laplacian of the 2 omega is equal to 0. So for the same reasons as before, because it was constant in time, it did not, the term had gone to 0. Similarly, because it's spatially uniform, the Laplacian of this, the second term, goes to 0. Hence, nu del square omega a is equal to nu del square omega. Hence, this is the reason why we have only omega appearing in these two terms and not the omega a. Okay, only this term has omega a. This is omega a. This is what we have defined as the absolute vorticity. So in the vorticity equation, in the rotating frame of reference has the absolute vorticity only in one term. So this viscosity term can have we can give an intuitive explanation of this, why this viscous term does not include the absolute vorticity, is because vorticity, the viscosity kills gradients in vorticity similar to how it kills gradients in velocity. So this happens when there is a relative motion between both the two different layers which are adjacent to each other. Now what happens is that when there is a solid body rotation, that is, something is moving, rotating constantly at a constant omega, the whole reference, the frame is moving at this constant omega, then there is no relative shear between the neighboring particles. So they are at rest with respect to the rotating frame of reference. So viscosity only damps out the relative differences, but if there is a solid body rotation and everything is rotating at a constant omega, and there is no difference in the vertical direction or even in any of the other directions, then the viscosity has no way to act on it because there is no gradient. Hence, if there is a constant rotation, there's a solid body rotation and it's constantly rotating at a constant at an angular velocity, which is, in this case, we have assumed it to be omega, then viscosity gradients cannot act on those particles. But of course, if there is a non-uniform rotation, then of course viscosity will kill the gradients in that absolute vorticity also. Okay. So this is this is an intuitive explanation of why we end up only having the Laplacian term in terms of the relative vorticity rather than the absolute vorticity. So there is one more term which needs an introduction in the case of geophysical flows, is called potential vorticity. So we have discussed the Kelvin's circulation theorem previously, and we mentioned that it does not directly apply to naturally occurring flows. This is because it is not a statement about conservation of a field like vorticity, first, and it does not apply for a baroclinic fluid. Okay, so we had said that it applies only in case of a inviscid fluid, and it should be homogeneous. So it cannot apply to a system which has a varying density, with density might be varying with depth, or it might be varying horizontally. So in naturally occurring systems where we have such density variations, and we see them routinely in atmospheric and oceanic flows, we cannot directly apply the Kelvin's circulation theorem. So in this scenario, we need to introduce an alternate concept of potential vorticity. So the concept of potential vorticity was first conceptualized uh, so first conceptualized by Carl Gustav Rossby. So this person Rossby we have already introduced, a scientist, and his name has also appeared in the Rossby number, and we'll also again discuss Rossby waves later in the course. And this potential vorticity was introduced by this person, and it was actually formalized by another scientist called Hans Artel. So Hans Artel was a German scientist who made fundamental contributions to geophysics and meteorology. So the term potential vorticity, I mean, this is the concept, but what does this concept mean? So the potential, generally represents, PV is a short form for potential vorticity that you might come across in geophysical fluid dynamics textbooks. So it generally refers to the quantity omega A dot gradient of theta by rho. So this is also called the Artel's potential vorticity. So omega A we know is the absolute vorticity. Theta is the potential temperature. And rho is the density. Okay, so we do not derive, the conservation of this quantity potential vorticity, but we state that this potential vorticity is conserved, and of course, if it is conserved, so this is the form of the conservation for potential vorticity. So it's this is a form which is not unique actually. I should mention this because there's a certain catch here. So this form is not unique. If theta is a materially conserved, the reason is being, I'm describing the reason. If theta is a materially conserved quantity, so is any function of theta. Okay, if theta is conserved, any function of theta is a quantity. It's a conserved quantity. Hence, omega A dot gradient of f theta by rho is also a conserved quantity and also can be called a potential vorticity, is also a form of PV. Hence, depending on the situation at hand or situation of interest, we will define potential vorticity according to that situation. So conservation of potential vorticity is of importance in rotating stratified flows in conditions when the effect of viscosity can be neglected and there is no adiabatic heating. In a baroclinic fluid, potential vorticity is conserved on isentropic surfaces, So but we'll not go into why that happens, but I mean we also not derive the form. So but we'll write down that the conservation of potential vorticity. So conservation of potential vorticity occurs in sorry um, occurs in inviscid adiabatic systems, adiabatic or isentropic systems. That is, it does not change heat to its surrounding, and it's inviscid. That is, we don't we neglect the effect of viscosity. In adiabatic isentropic systems, in baroclinic systems, this conservation of PV occurs on isentropic surfaces. So one of the ways we can get rid of viscosity in the flows is because in large scale systems, viscous forces are negligible, as if we are away from boundaries, as we have mentioned in the previous lectures also. So this non-conservative viscous forces are very small in magnitude compared to other terms in the equations, and then we I mean these are the conditions where we neglect neglect viscosity, and hence these flows are characterized by conservation of potential vorticity. Now I want to mention something which is related to conservation laws in physics in general. This is called the Nodus theorem. So this is called the Nodus theorem. Some people also call it Noether's theorem. So this says that for every continuous symmetry in a physical system, for every continuous symmetry in a physical system, there exists a conservation law. Okay, so this is a profound theorem that was discovered by German mathematician Emmy Noether. German mathematician Emmy Noether. So she discovered that if a system has a symmetry, there must be a specific quantity like energy or momentum that stays constant with time. That is something should be conserved in the system if there is a symmetry, and this routinely shows up in the things around us. And sometimes we may not realize that this is because of the inherent symmetry in the system. This is something very common to us, is that we as physicists and engineers have come across, is the conservation of energy. So conservation of energy, and all of these can be proved using techniques that will not go in deep into. So this conservation of energy is it says that the laws of, I mean the energy is conserved in a system, in an, of course, an isolated system where there is no exchange. So this corresponds to a symmetry which is there in all physical systems. So this corresponds to time translational symmetry or time translation symmetry. What does it mean? That is, laws of physics do not change from one moment to the next. Let's say you do an experiment at 10 a.m. today, and then you do the same experiment at 5 p.m. Exactly the same experiment, keeping everything same, all the parameters same. The laws of physics don't change. It does not matter what is your starting time, what does the time of your clock says. The laws of physics will remain the same. So there is a time translation symmetry, that is, you do it at 10 a.m., 5 p.m., 12 a.m., it does not matter. It just is oblivious to the time of your clock. So this symmetry gives rise to a corresponding conservation, which is the conservation of energy. There is one more conservation law which we regularly come across, and this is conservation of linear momentum. And by Noether's theorem, there must be a inherent symmetry. So what is the inherent symmetry? The symmetry of the system is the spatial translation symmetry that corresponds to the conservation of linear momentum. Okay, so what does a spatial translation symmetry mean? It means that the laws of physics don't change where you measure it. Okay, you can measure, you can do an experiment in one corner of the room, you can do the experiment in the center of the room, you can do the experiment in your terrace or in your garage. It does not matter. Your conservation, the spatial translation symmetry, it does not matter where you take it. So and it does not matter from where you measure it. This corresponds, this translational symmetry corresponds to the conservation law, which is the conservation of linear momentum. The other conservation law that we come across is the conservation of angular momentum. Okay, so this means, there should be, by Noether's theorem, there should be symmetry in the system, and the corresponding symmetry of this conserved quantity is the rotational symmetry. Okay, so rotational symmetry means that the physics remains same even if we rotate our experimental setup. Okay, so it does not matter in which direction you are measuring, or let's say there's a channel flow from one direction to other. Even if you rotate it and the flow starts going from here to here, there is no change in the physics of the problem. So for an isolated system, rotational symmetry corresponds to the conservation of angular momentum. Now we were discussing potential vorticity. The conservation of potential vorticity exists because of something called the particle relabeling symmetry. Potential vorticity is conserved because of something called the particle relabeling symmetry. So what does this mean? In Lagrangian description, we identify individual particles using an initial coordinate. Okay, so drawing something that we have drawn previously. So there is an initial coordinate, and this is a1, a2, a3, and we identify. So this is the initial coordinate, and the position is given by, the position at a certain time is given by, let's say, calling it x. X is dependent on the initial coordinate from which we started out with, and this is the trajectory of the particle. So what does this particle relabeling symmetry mean? The symmetry means that if we relabel these particles using a different coordinate system, the equations of motion and underlying physics remain the same. Okay, so this is based on a certain coordinate system, let's say something like this, and then you want to relabel, just drawing it slightly better. So if you want to relabel, let's say you want to create a new coordinate axis, and you want to relabel the particles based on that coordinate axis. So the physics of the problem does not change, and because there is this inherent symmetry in the system, and we can relabel these particles using a different coordinate system, the equations of motion and the underlying physics remain same. And that is the reason, because of this inherent symmetry, this potential vorticity is a conserved quantity. That is, this symmetry corresponds to conservation of potential vorticity. Okay, for a baroclinic fluid, however, these transformations from one coordinates to other must be constrained with mass conservation, and relabeling is allowed within the same isentropic surface only.